Thanks. Welcome back, everybody. Um, so, just again, you guys did pretty good last time, but I'd actually appreciate it if you interrupted me even more. Okay, so I challenge you to find a question that I don't know the answer to. Those are always the best questions, right? Okay, so I just want to. There's one thing that I didn't quite finish last time. Last time we were talking about this sort of refined power counting that takes into account factors of 4 pi and allows some differentiation between strongly and weakly coupled theories. And just to remind you, this G star is a coupling strength that I argued should be between 0 and 4 pi. It's dimensionless coupling strength. And M is supposed to be the scale where this theory breaks down, okay? So I just want to point out that if we consider the case where this phi is a scalar, which is actually what I've written here, then if I just use this power counting, you can check that the kinetic term has an order 1 coefficient, so that makes sense. But then the mass has a coefficient of, guess what? M squared, okay? So this is, again, inconsistent, okay? This is inconsistent because we're supposed to be describing a light scalar. So this counting doesn't work for the quadratic term. It also doesn't really work for the cubic term, okay, because this is also proportional to M. So maybe if G star was super small, but this is also in danger of being a strong coupling, okay? And then after that, it starts to make sense, okay? So I'm just pointing out that we're seeing the same thing over and over again, right? We see that somehow the ways we use to make sense out of effective field theories don't seem to work for scalars, at least without any other, with minimal ingredients, okay? So that's all I wanted to say about that. Just wanted to point that out. So any questions on anything up till now? Okay, you can always come back. So now I just want to, we're here, okay? But now for these 3 topics here, I'm going to be bouncing around between these 3 topics because they're actually very closely related to each other, as I'm going to try and show, okay? So, but we're going to start with a very basic discussion of symmetry, okay? All right, okay. So hopefully you know what symmetry is, okay? It's some kind of a transformation that acts non-trivially on the system, but leaves some things invariant, right? That's sort of what the idea is, okay? So the first thing I want to do is I want to distinguish symmetry from gauge symmetry. So I want to talk a little bit about gauge symmetry, because very often what we say is that, for example, the standard model is invariant under a gauge symmetry, okay? The point is that what is a gauge symmetry, quote unquote? What it is this is actually a redundancy whose purpose is to eliminate degrees of freedom. Okay? So, for example, if we look in QED or in any abelian gauge theory, we look at the gauge field. We have 2 gauge field configurations that are related by a gauge transformation, okay? And the claim is that A prime and A are physically equivalent, okay? And if I add some, say, charged fermions to the theory, now the gauge transformations also act on the fermions, but the primed field configuration is physically identical to the unprimed field configuration, okay? So I've prepared a lecture demonstration for you, okay? I've borrowed this from the late, great Sidney Coleman. So here's a glass of water. Now I'm going to perform a gauge transformation on the glass of water. Okay? So that's a gauge transformation, so remember that, okay? On the other hand, you know, a translation of the glass of water could be like this. A rotation could be like this, right? So that's the difference, okay, between a gauge transformation and what I want to call a symmetry, right? And so we know very well that, you know, about this eliminating degrees of freedom, the number of field components of a gauge field is 4, but the number of physical polarizations of a physical photon state is 2. And so the gauge redundancy's purpose in life is to allow us to describe a 2-component object with a local field that has 4 components. Okay? Yes? Yes?
So what if I choose my omega so that I make A prime 0?
Very good. I'm going to come back to that, okay? So hold on to that thought, okay? Actually, why don't I just do that now? Okay, I was going to do that in a little bit. I'll do it now, just for you, okay, my friend. Okay, so the thing is that you would say, okay, now this question has several layers of subtleties, okay? But you're going to have to, if you want me to go all the way into all the subtleties, you're going to have to force me by asking me the right questions, okay? Otherwise, I'm going to just tell you the simplest version of the story, okay? So yeah, so what happens if omega of x is a constant, okay? That's what you're asking. It's a great question. So what happens is that the gauge field no longer transforms because the derivative of omega is 0, right? But for example, the fermion fields still transform, okay? So now I can just look at this and I can say, well, this is a global symmetry of the action, right? Okay?
Sorry, that was actually not my question.
Oh, okay. Then maybe it wasn't a good question.
No, my question is if the function omega is so that when you sum with A mu, you make A prime mu equal to 0.
Oh, so in that case, then if you can make A prime equal to 0, then your starting gauge transformation was also trivial, even though it doesn't look trivial. If it's a total derivative, for example, in fact, so in U1 gauge theory, we know that the physical electric and magnetic fields are contained in the field strength tensor, right? Okay, which is an antisymmetric combination. And you can just see that if omega was a total derivative, which means that you can get rid of it, then the field strength vanishes identically. So the electric and magnetic fields vanish identically. Okay? Yeah. Okay. All right. Okay, but since I started on this, I'm going to keep going, okay? It's still a good question, okay? So you can look at this special case, right? You can look at this special case, and you can say that, let me just look at this, and now this looks for all the world like a symmetry, right? And in fact, you can just use apply Noether's theorem, right? You can just apply Noether's theorem to this, and guess what? You find that there's a conserved current, okay? And this current is exactly psi bar gamma mu psi, okay? All right? So you would say, what are you talking about? What are you saying this is not a symmetry? It implies a conservation law, in fact, a local conservation law, okay? And it's true, it does. Electric charge is conserved, right? And it does do that. But what I would claim is that, and in fact, in the Lagrangian, the interaction term in the Lagrangian is just the gauge field coupled to precisely this Noether current, okay? But what this is telling you, in fact, is that this conservation of the current is just a necessary consistency condition for having a gauge field. If you want to have something that has a massless field that has 2 polarizations, then it has to couple to a conserved current. And in Utin's lecture, right, you saw that coming out in a different way in terms of on-shell states. This is how it comes out in a more conventional field theory language, okay? So I also want to point out that this makes it sound very formal. Oh, what's the sound? It's some kind of, you know, some kind of jujitsu, formal jujitsu here. Yes? Sure. Zero dies pretty quickly at infinity. Yes? Yeah, omega. Right. Oh. Actually, it only has to die out to infinity up to a total derivative. So when you're doing things like instantons, you precisely are requiring that it, for example, in the non-abelian case, what you have to show is something like G inverse d mu G, okay, is dying sufficiently at infinity. But that, again, involves a derivative. Okay, so constant gauge transformations are perfectly okay. Okay? But see, like I said, this all sounds like some very formal jujitsu, okay? Let me just tell you very, very physically, why did this happen, okay? So why is this happening at a more elementary level? It's because of Gauss's law, okay? You may have heard of it, okay? So imagine I have some region where I have some charge localized in some region, and I'm very far away. Then I draw some Gaussian surface like this, okay? And it's a fact that if I take dA, if I compute the flux, total flux around the surface, I get the total charge inside, right? You know this. But what you may forget is that this thing is working, this thing is happening at some constant time, okay? But this is not some non-relativistic approximation. This is an exact statement in Maxwell's equation, okay? And so this can only be consistent if you could change the charge in here, you would instantaneously be changing the field at this Gaussian surface. That's clearly impossible. So not only you have to conserve the charge, you have to conserve it locally, because if you take a charge here and it instantaneously appears on the moon, you're still screwed, right? Because it's the charge inside, okay? So local charge conservation is just a consistency condition that we get for free for requiring that we have a photon, okay? All right? Okay, so that's what I would say is the sort of the status of gauge symmetries, okay? Now, the reason I was going to do this afterwards is I don't know, people don't usually say things this way, so I don't know if there's a standard language for this, okay? But I would like to say that this is an accidental symmetry, okay? And so this might raise a few hackles, which is why I was going to do this a little bit later, because there's something else that's called accidental symmetry, and this doesn't quite look like it, but actually, I'm going to talk about that next. You'll see it is the same thing, because really what accidental symmetry is the idea of accidental symmetry is that what I impose, okay, are just the gauge symmetries of the problem and nothing else, because those are the things that I need to have to get the right degrees of freedom. And then the accidental symmetries are the ones that I get for free, okay? So at least under that definition, this is just an accidental symmetry, okay? All right? So while we're on the topic, since you've gotten me out of order, okay, let's talk about another accidental symmetry of the Standard Model that probably nobody told you was an accidental symmetry. It's called Poincare invariance. Symmetry, well, whatever, yeah. Okay? I claim that Poincare symmetry is an accidental symmetry. Why? Because we have general relativity, okay? And in general relativity, the metric, the space-time metric, is a gauge field, okay? And I don't mean that it's secretly an A mu. What I mean when I say that it's a gauge field is what I mean is that this field, the number of components in the field G mu nu, because it's a symmetric tensor, right? It has 10 degrees of freedom, okay? But a single physical graviton has 2 degrees of freedom, as we heard from Yutin's lecture, right? And so there is a redundancy, which I can just think of as a gauge symmetry, because I don't know what else to call it. In fact, well, anyway, it's a gauge symmetry. And it is just what you could call the diffeomorphism invariance of general relativity, right? So if I take these two metrics, G and G prime, defined in this way. So the gauge transformation is x prime mu as a function of x, or equivalently x mu as a function of x prime. They have to be invertible, so they're both well defined. And then picking one of these, that's the analog of my omega, right? My omega, which depends on x. And so these are the gauge transformations, okay? And this cuts down the number of physical degrees of freedom. Yes? Hi.
The second line, you didn't understand. Can you repeat, please? I mean, the cat equals to 2.
It just means, this is a very, very shorthand. Just like here, what I mean by this number is how many polarization states there are. So these are the two polarization states for any massless particle of any spin in 4 dimensions. Yeah. Was that your question, or was there? You're still confused. Well, I just explained it. I don't know what the problem is. I'm kidding. No, go ahead.
Is the degree of freedom? Okay, you have 2 degrees of freedom, correct?
Yes.
Okay, but this degree of freedom is from the space-time, from...
It's in the field G mu nu. So G mu nu is a field, right? And so just like, if I was expanding around flat space, I would just write this in terms of some polarization vectors and some creation and annihilation operators, very similar to a gauge field. Yeah, okay? Good. Okay, any other questions? This is not a course about gravity. This is just some, this is culture, okay? So the key thing here is that this theory has no preferred metric, right? So when you open the first page of your quantum field theory book, they tell you that the metric is called, well, I call it eta mu nu because I don't want to call it G mu nu, okay? But anyway, it's just the standard Minkowski metric. But there is, in this theory of general relativity, there is no preferred metric. There's no Minkowski metric. There's no Minkowski invariance. There's just this gauge invariance here, okay? So in fact, what metric we actually have comes from solving the equations of motion, right? And in fact, we know that on the grandest scales, we have some cosmological solution, which certainly is not exactly flat, right? But the basic point is that, the metric that we have, the metric is in fact just a solution, right, to the GR equations of motion, right? Okay, so we have to solve the equations of motion to find out what the metric is, okay? So now gravity, just like everything else, is an effective field theory, and now I'm writing down the action. So what does the action for gravity look like? We write down the most general thing that we can compatible with this gauge symmetry. That's what we're doing. Okay, and the first thing is that you see that if you want to make things invariant under this transformation in a sense acts on the x's, and so you have to include this power of square root of determinant of the metric in order to make even the measure, the space-time measure, invariant under this gauge transformation. But then you can just start adding things. So I'm going to add some constant term, and then the next thing, and this, if you like, is a dimension 0 operator, right? Because this is like the identity operator, okay? Then I can have m Planck squared, and then the next thing that I can write is the Ricci scalar, okay? And that you can say is dimension 2, okay? And so on. And I can start writing higher things, okay? All right? Now, this is the infamous cosmological constant term, and what we know about it is that it's insanely small, okay? Okay, because this is identified with the Planck's, this is the Planck scale that gives us the Newton's coupling, right? But if this cosmological constant is non-zero, then it gives us some curvature, let's say today, like the Hubble constant, which would be like lambda squared over m Planck. That's just a fact about general relativity, okay? And we know that this is incredibly small, right, compared to the scales we're interested in. And so the point is that we know, just from the fact that you and I are talking, for example, or anything makes sense, that we know that this lambda is very small. Okay? We'll say more quantitative things about that later, but right now I just want to say it's incredibly small. That's just an experimental fact. And this fact, well, we don't know why, we have no idea, okay? That's important, but it is a fact, so let's just put it in for now. And then what we find is that the maximally symmetric solution, which is, okay, is that g mu nu of x is approximately eta mu nu, okay? All right, in other words, the most symmetric solution you can write is very, very, very flat. And this is exactly Poincare invariant, okay? Of course, we know it's not exactly true on cosmological scales, blah, 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 okay? But so I would claim that even Poincare symmetry is just an accidental symmetry in exactly the same way. It arises because we have certain degrees of freedom automatically, okay? Okay, any questions on this? This is all I was going to say about this for now, okay? Okay, so, all right. So in fact, as we'll let me just say what the punchline is going to be about this is that, you might have often heard people grandly proclaim that in string theory, or even more grandly in quantum gravity, there are no global symmetries. There are no ungauged symmetries. Well, the same thing is true in the standard model, okay? Okay, that's going to be the punchline for this. Okay, so now I need to go back. I actually need to talk about what is more conventionally called accidental symmetry, okay? So let me do that. Okay, good. So let me talk about the more conventional form of accidental symmetry. Okay. Okay, where it has nothing to do with gauge symmetry. Okay, and logically this should really come before what I said there. But now imagine I was very far away. I'm off on the horizon. What do I look like? I look like a dot, right? And that dot looks like it is rotationally invariant. But if you look at me, I'm not rotationally invariant. I mean, I'm working on it. I'm eating these big lunches every day, but so far, I'm still not quite, okay? And so in fact, this seems to have an SO3 symmetry, right? If I'm far away, I look like I have an SO3 symmetry. This is an accidental symmetry. It's only approximate, okay? And it has to do with the existence of a hierarchy, right? My size is small compared to the distance away, okay? That's actually the canonical simple example of an accidental symmetry. Now, a more respectable one that you could talk about in a physics class is, again, our friend, the multipole expansion, okay? So if we look at the multipole expansion, remember we have some charges localized here. I have some faraway place here. So the size of the charge distribution is A, R is much bigger than A, and I'm asking about the electrostatic potential here. The first term, I have the monopole, then I have the dipole, and then I have the quadrupole. I can do this, okay? And as I talked about last time, when R really is bigger than A, then these are getting smaller and smaller, right? And an expansion in powers of A over R. But notice that this one has an SO3 symmetry. It's rotationally invariant, okay? This one here has a single preferred direction, right? Because of this, because QI has to point in some direction, right? So Q1, say, maybe points in that direction, say. So it definitely breaks the rotational symmetry, but it still preserves an SO2. It preserves the rotations around that dipole moment, okay? And then, if I have a generic quadrupole moment, I don't have any symmetry. So what you see is that as you go to higher orders in this expansion in A over R, you're getting sort of less and less symmetry. But at the leading order, you have some symmetry, okay? So this is what is meant by accidental symmetry, okay? So now, this is very important in quantum field theory. I'm just going to erase this, okay, to use this board. Okay, so let's give a simple example of this in quantum field theory, and I'm just going to use QED. Okay, so the game is we're going to write down QED the way we think about an effective field theory. Okay, we're going to write down the most general Lagrangian that's invariant under U1 electromagnetic gauge. Yeah, yeah. That's true. That's true. You're right. That's a good point. So R2, yeah, thank you. Ri, Rj, R, wait, no, it's R to the, yeah, because R is positive. Well, R is always positive, so, but you're saying some kind of an inversion symmetry. I think you may be right. I think there might be some kind of discrete symmetry left over. Good homework problem. What is the symmetry of something that has, well, but remember, if it has both a dipole and a quadrupole, if they're not aligned, are you sure? Maybe there's still, I'm not sure either. It's a homework problem. Yes? What? Yeah, it's probably parity. I think you're probably right. Yeah, I think it's parity. Okay? Okay? Yeah, in fact, I know it is, okay, because I'm about to show that. Because we're doing QED, okay? All right? So yes, it's parity. Good. If I had, Mark Wise, when he teaches, he tells me that he has a bowl of candy, and he always throws candy out to the students that ask questions. So you get an honorary Mark Wise candy, okay? All right, so we're writing the most general Lagrangian that we can that's invariant under U1 gauge transformation, and that, of course, means that we have some associated gauge fields, A mu, and then this thing has two fermions. So I'm using Weyl language, okay, because Weyl fermions are the fundamental building blocks. Okay, so I have a left-handed and a right-handed fermion, and the only thing I have to tell you to define the theory is that they both have the same charge under the gauge group. That's it. That's the definition of the theory. Okay. The standard model has a similar definition. It's just that there are more fermions, there are more gauge fields, but it's the same idea. You just define what are all the fermions, you define how they transform under the various gauge groups, and then we also have the Higgs, right? The thing we don't understand. Okay, so let's just write down what we can, and we can write down a relevant term, which is a mass term. Okay, so this has dimension 3. It's a relevant term. Then we can write down some dimension 4 terms. Okay, we can write down a kinetic term for the left and the right-handed guys. Okay, and we can write a kinetic term for the gauge fields. Okay, and these are the dimension 4 terms, and then we can keep going if we want to dimension 5. Okay? All right. Okay, so now this is not the way that it's usually written in the textbooks, right? You can, if you want, combine these fermions into a Dirac spinner. So I'm going to call that by capital psi. And I know that capital psi looks a lot like little psi, but that's not a problem. Howard Georgi always says that notation should be your slave, not the other way around, right? Okay, and so here, capital psi is just putting these two things together, these two-component spinners into a four-component spinner, okay? Now, can we put this term right here? Notice the way I've written it, this is this plus the complex conjugate of that whole thing, so I'm not assuming that M is real. Okay, because I'm being as general as I can, okay? But it's easy to see that I can rephase psi L and psi R independently to absorb any phase in M, okay? So the claim is that I can rephase psi L and psi R so that M is real, okay? You okay with that? It's just a redefinition. It's just, that's totally fine. And then, having done that, then this M psi L bar psi R plus emission conjugate becomes the way that you've normally see it written in textbooks in terms of the Dirac field, okay? Okay, so what is the deal with Dirac versus Weil here? What's going on? Why do we have these two different languages, okay? So I claim that there's, here I've written all the possible terms that I can up to dimension 4. Yeah, sorry. No, I mean, M is just, I mean, you know, M is just a coupling constant. It's just some number, okay? And so I would claim it's kind of just going into a basis where M is real. The fields are the psi's, and I'm, in the path integral, if you like, I'm integrating over all possible psi's. So integrating over them with some phases, with, you know, shifted by a phase is exactly the same. Yeah, it's just a change of basis in a path integral. I think that's the easiest way to think about it. Okay? Just change of variables in a path integral. It's always okay. Okay? Okay, so the claim is that this Lagrangian is accidentally invariant under, you guessed it, parity, okay? Which is why that theory also has a parity invariance, okay? In fact, to all orders, it's just an exact symmetry, because it's an exact symmetry, well, sorry, not, okay, it's, okay. This theory, up to dimension 4, has a parity invariance, okay? And how does parity act? First of all, let me just remind you, parity, what is it? It's actually an extension of the Lorentz group. It's an improper Lorentz transformation. When I say Lorentz transformations, what I mean are rotations and boosts, okay? So you cannot make a parity transformation out of rotations and boosts. It's really an additional assumption, okay? An additional, but I can think of it as a Lorentz transformation just in the sense that it is a, you know, it's a 4x4 matrix that acts on 4 vectors, okay, like this, okay? That's the, okay? And of course, this is only one example of a parity transformation. I could do this and then do lots of rotations and boosts and get lots of other disconnected Lorentz transformations, but this is the one I'm going to focus on, okay? And then how do these fields transform under this? Well, I'm going to tell you the answer in the Dirac notation, okay? In the Dirac notation, this is just, you can look at this in your favorite textbook. If you look, how do things transform under this? There's some gamma 0, and there's psi of lambda p x. Okay, so that's how the Dirac fields transform. Okay, and in terms of the psi L and psi R, this thing, what does this thing look like? It looks like psi R, psi L. Okay. Now, in the Weil language, parity is very confusing. Because, for example, if you're using an index notation, psi L and psi R have different index structure. So I have destroyed the index structure here. Okay? Are you worried? Should I be worried about that? Usually, if I mess up the index structure, you know, somebody comes over with a hammer and starts hitting you, right? Well, remember, I've extended the Lorentz group, okay? So yeah, okay, I've extended the Lorentz group, and it actually mixes the left and the right-handed guys, or reverses them, okay? So the lesson here, first of all, I think this should be emphasized a bit more, I should really think of a Dirac fermion as a parity multiplet, right? Just like, you know, if I do a symmetry transformation and I get new stuff, I have to add it to get the full multiplet, right? The same kind of idea here. Okay, so this makes perfect sense. It's actually true, and you know this is the famous parity invariance of the QED Lagrangian, which is also the parity invariance here. Okay, all right, and I didn't ask for that. I didn't impose it. It just came. Okay, now, but once I go to higher orders, if I say why am I stopping at dimension 4? In fact, I know that QED is not the whole theory of the universe. It's embedded in the Standard Model. And I integrate out things in the Standard Model, and actually, I will generate higher dimension operators that violate parity. Okay, so you can write down operators. I'll just write it in the Dirac-Lagrangian, Dirac way. I could write down something like this with a gamma 5, okay? And this violates parity. Dimension 6, and in fact, this operator and a bunch of other operators that violate parity are generated at dimension 6 if I integrate out the W and the Z. Okay? So that is a very canonical example of accidental symmetry. Okay? Yes? Well, I mean, we care about parity because if it's a good symmetry, it helps us understand what's going on. So we certainly care about parity. The question is, maybe your question is, why do quantum field theory books, not put Weyl fermions on a higher pedestal? And as I said, I'm writing a quantum field theory book, and our book is doing just that. Okay, so I think you're right. That's what how it should be, especially nowadays because. The frontier of calculating amplitudes, a lot of it, as Yutin is teaching us, uses these on-shell methods, and these are particularly powerful for massless, massless fields, and that is also a very, very good approximation at colliders like the LHC, right? And so, this is an extremely active field of research, and so I think that it is time for quantum field theory books to catch up with that. To break Lorentz invariance? I think you made a joke and I didn't get it. I'm sorry. Oh, well, there's a gamma 5 here. Yeah, okay, right. We don't accidentally break, thank you. We don't accidentally break Lorentz invariance. Good, okay. Oh, wait, I broke it again. I didn't lower the index, huh? Okay. Okay, all right, and so this is the point in the discussion where logically you should insert now the discussion about the quote-unquote accidental symmetries that come from gauge transformations, okay? And so at the end of the day, the claim is that all of the symmetries, all of the symmetries, in my sense, of the Standard Model are accidental, okay, including even Poincare invariance, okay? So sometimes when you learn about symmetries, I've found that students always ask, well, where do they come from? Did God tell you? Like, who tells you there's a symmetry? And in fact, historically, it's kind of how it happened, except God was like Murray Gell-Mann or something. In other words, somebody just said, symmetry is beautiful, okay? And so therefore we have symmetry, okay? But now we have a better answer, okay? Everything that we know, this is what I'm going to be talking about here, and the reason I'm bouncing around here is that I'm going to try to tell you in this part that really we understand everything within the Standard Model incredibly well, okay? So for example here, I'm telling you we understand that all the symmetries of the Standard Model are simply accidental, okay? But then you can ask, okay, wait, but there's a whole lot more going on in the Standard Model, right? So far, every example of a quantum field theory that I've showed you that has a hierarchy, it's unnatural, right? But we have tons of hierarchies within the Standard Model, all right? But what I'm going to show you next, what I'm going to try to explain next, is that there's no problem whatsoever within the Standard Model. All the hierarchies make perfect sense, okay? In the same way that other kinds of physics make sense, okay? So that's the next thing I'm going to try to explain. Okay? Okay, so I'm going to talk about naturalness. Okay, so I'm not done with 2. I'm going to come back to it, as I said, but we're now on topic 2. Okay, so what do I mean by naturalness? Okay, well, thinking about this, I think the best way to explain what naturalness is to explain what unnaturalness is. Okay, so let me explain that first. Okay, and I'm just going to explain with some examples. The first thing I'm going to talk about is the Heisenberg model, not the horrible Heisenberg model in particle physics, which hopefully none of you know what it is, but the more famous lasting contribution Heisenberg model, which is a condensed matter model. Okay, it's a spin model. So I have a lattice, right? It has some lattice spacing A, and on each site, I have a quantum spin, okay? So you can think I can have a spin 1/2 particle at each site. So this is a quantum mechanical theory. And I just have some nearest neighbor couplings between the spins on neighboring sites, okay? So this is some quantum mechanical model where if J is positive, this interaction wants to make the spins line up, okay? All right, it's like the Ising model, except it's a honest-to-goodness quantum theory, okay? So what is the physics of this model? Okay, essentially what I'm saying is pretty much true in every dimension, I think, except one. Okay, but this is very qualitative, so you behave yourself. Okay, so what is the qualitative physics of this? Well, let's think about it as a function of the temperature. Okay, so I could look at the spin-spin correlation function in this theory, and generically, what does it look like? Generically, it's going to have, sorry, this is an R, so I'm looking at the correlation between a spin here and a spin here, separated by some vector R, say. Okay, these are vectors, I guess. Okay, the x's are vectors. All right? And generically, it falls off at large distances, it falls off exponentially, right? And this xi is called the correlation length, for obvious reasons. It measures the characteristic length scale over which correlations die off, okay? And so as a function of temperature, for generic T, okay, then the correlation length is just of order the lattice spacing. In other words, once two spins get even a couple of lattice spacings away from each other, they're completely uncorrelated. Okay? And so there are no long wavelength correlations. There's no hierarchy in my language, right? Right? There's no hierarchy of scales. Yes? Finite temperature, yes, finite temperature, okay? But generic, well, I'll tell you what I mean by generic. There's a non-generic temperature. there's a phase transition in this theory, okay? At some temperature, T equals T star, okay? There's a second order phase transition. Okay? And in the second order phase transition, what happens is that as T goes to T star, let's say T approaches T star, xi actually goes to infinity. Okay, the correlation length diverges. Okay? And how does it diverge? There's a famous formula, okay, or behavior. So this is the fractional difference away from the critical temperature. It's normalized to the lattice spacing, but then this thing, there's some power, okay, that this diverges as some power of the distance, you know, sort of the distance that you are away from the phase transition. This thing is called a critical exponent. This thing nu is called a critical exponent, okay? And nu, I should have looked up what it is, but it's some number, it's order 1, and it's, you know, it's some number of order 1. Maybe it's 0.5. I don't know what it is for the Heisenberg. I guess it has to be Ising in 2D, but anyway, it doesn't matter. I don't know what it is. But it's okay? And so here what we see is that, wow, great, we actually do get a hierarchy, right? But there's a price. The bigger that we want the hierarchy to be, the closer we have to choose the critical temperature to be, the temperature to be at the critical temperature, okay? So we can have xi much bigger than A, we can have a hierarchy, but it requires tuning, right? It requires tuning. Tuning what? Tuning the temperature, right? Okay? So for example, if you're a condensed matter experimentalist and you have a chunk of your Heisenberg model, okay, well, it won't be exactly the Heisenberg model, but this is a pretty good model for some real spin systems, and you know it has the second order phase transition, so you stick it in your oven, okay, you get it to some temperature, and you take it out, you know, and you put it in your measuring apparatus, and I don't know what you do, but somehow you measure the correlation length. And you find that it's 10 billion times the lattice spacing. What do you think the chances of that happening are? Well, if you did it 10 billion times, maybe that would happen, okay? But you get my point, okay? Of course, that's not what experimentalists do. They very carefully change the temperature by little units, and they try to close in on the critical temperature, right, to study this very interesting phase transition, okay? All right? So that's an example of tuning. We can get a hierarchy of scales, but we have to tune a parameter, okay? And this T star is actually extremely hard to calculate. If you want to start with this Lagrangian and try to calculate T star, it's very difficult, okay? All right? So it's a very active problem in condensed matter physics to calculate critical temperatures or even understand phase transitions. Now, this is a very standard sort of phase transition, okay, that you read about in textbooks, okay? One last thing I want to say about this. Usually people talk about this, they talk about the Ising model. I purposely did not talk about the Ising model. Remember, this is a quantum theory, okay? So what I want to say is that if we are tuning close to this thing right here, this is a quantum theory with a long correlation length, right? So this is starting to look like the quantum field theories that we're really interested in this course, right? Okay, so I'm going to give another example, which are the cuprates. You didn't think you were going to learn about cuprates, and you're not, okay? But I'm going to just say some very qualitative things, okay? So what is the deal with cuprates? Cuprates are much, much more complicated materials, okay, and they have a very complicated phase diagram, which I'm going to just sketch for you. There's temperature on this axis, and there's x, which is doping fraction, okay? And doping fraction means that I have some kind of an impurity. I think it's copper. I think that's why these are called cuprates. I think it's copper, but anyway, it's something. And you know, you can decide what the average amount of copper you have, right? And then you make your sample and it gets, okay? And so there's a phase diagram as a function of the temperature and the doping fraction. And I just want to emphasize that the bottom of this graph is 0 temperature, okay? And this is a subject of active investigation, but if you go look up what people think happens in these theories, it's something like this. There's an antiferromagnet here, and then there's some superconducting phase here. There's some weird phase here, which they call something like a non-normal metal or something, I don't know. Anyway, it's a complicated phase diagram, okay? But what I want to call your attention to is that there are phase transitions at 0 temperature. At 0 temperature, okay? All right? So I don't think these transitions are very well understood, okay? But so that means I get to make up a fairy story, and my fairy story is that one of these things, like this one, for example, is a second order phase transition, okay? Maybe they even know that this is not true, okay? But I'm just going to pretend that it's true. There certainly are these 0 temperature phase transitions. Now, this is something which is a lot more like a quantum field theory, okay? Because the experimentalist makes their sample, okay? I'm sure it's quite a bit of work to make a sample. And then they're going to end up somewhere on this line, okay? And if they're really lucky, they might be sitting very, very close to this phase transition point, right? Now, them making this sample with a different doping is like changing the theory at the lattice scale. It's kind of changing the quote-unquote fundamental theory of this thing. But if there's a second-order phase transition, then I again expect the correlation at 0 temperature, right, T equals 0 phase transition. Then I expect to, again, have a divergent behavior now as a function of the doping fraction at 0 temperature with some kind of critical exponent. I'll call it nu sub x. Okay, just like I have over there, okay? And so as x goes to x star, which is tuning, right? I have to work very hard. If I wanted to get very close to X star, I have to get lucky or try a lot of times. Then I will find that the correlation length diverges, okay? And so here, what I claim is if I have xi much greater than a, so suppose I'm able to make the doping fraction very, very close to X star so that I have a very large correlation length, then the long-distance physics of this theory is exactly described by a quantum effective field theory. It's a quantum theory because this is a quantum theory. It's the quantum spins that are the main important degrees of freedom here. And it has a long correlation length, and it can be described by a quantum field theory, okay? Not Lorentz invariant, right, but a quantum field theory, a non-Lorentz invariant quantum field theory, okay? All right, but again, this is an example of unnaturalness, right? You cannot just walk into a room and expect, somebody, the first sample you make is not going to have a correlation length much larger than A, unless you get incredibly lucky, right? Is it clear? Okay. Okay, so what I'm trying to say here is that this phenomenon of unnaturalness is something that is very, very well known, very well understood in condensed matter physics. It's not some exotic, weird thing that particle physicists made up, okay? Okay, but now let's actually talk about quantum field theory, okay? Let's look at unnaturalness in quantum field theory, which we actually care about, okay? And just like I talked about EFT from top down and bottom up, I'm going to do the same thing with the concept of tuning, which is sort of an EFT concept. And I'm first going to start with the top down picture, okay? Because in the top down picture, everything is very concrete. So let me tell you what my fundamental theory of the universe is, okay? It has a scalar, okay? And it has a fermion. That's it. That's all it has, okay? Let's say it's a Dirac fermion. But the Dirac fermion has a large mass, okay? And now, since I'm going to be interested at loop level, I'm also including some counter terms here for this theory, okay? And so my intention is that the phi mass is supposed to be much smaller than the psi mass. Okay, I'm trying to have a hierarchy here. So what I have in mind is that phi is something like the standard model Higgs boson, and this m is some fermion that's part of a grand unified multiplet, so it's at some much higher scale. Okay? All right, that's my theory. Okay? And so now what I want to do is I want to find the effective theory, right, by integrating out the heavy fermion. All right? So at tree level, it's very simple. At tree level, I just ignore, oh, sorry, I don't have an interaction. Sorry, I want to have an interaction too. Sorry, I have an interaction. Okay, I have an interaction, a Yukawa interaction. That's very important, okay? So at tree level, I can, at tree level, I don't have anything. I just cross off the psi. There are no diagrams that only have external phis that have know about this interaction, okay? But at loop level, I do get something non-trivial, and that's why I have to keep the counter terms. Okay. So, so what am I going to do? Okay, so what I'm going to do, since I'm interested in the mass, let me look at the two-point function, and I'm going to equate the two-point function of phi in the fundamental theory and the EFT, right? Remember, that's my matching. That's what defines the effective field theory, okay? And so let's just start calculating what's this. So I'm calculating the 1pi effective action. So the first term is just like this. And this is just equal to I, p squared minus m squared, where this is the momentum flowing in here, okay? And then the next first non-trivial thing that I see is a one-loop correction like this. okay? And that thing is going to be UV divergent, okay? So I'm going to have to put in the fundamental theory, I'm going to have to put in a counter term like this to make it finite, okay? And then there are higher order diagrams which start at y to the fourth, okay? All right. Okay, and what about on the other side, in the EFT, I don't have any interactions of phi in that Lagrangian that don't involve phi. So I just have this term right here, which is, this is the EFT, I'm calculating this blob, right? And this is just equal to I p squared minus m squared. Okay, so I'm writing the EFT. I'm writing the EFT as 1/2 delta phi squared minus 1/2 m squared phi squared, okay? Plus, well, more stuff, okay, that I'm trying to calculate, right? Okay, so this term gives me just this, okay? And then, I don't have anything else, right? I mean, there's no other diagrams I can draw here, except that I can draw a counter term, okay? And so there's going to be some kind of a counter term in the EFT whose purpose is to match the fundamental theory. Remember, right? That's renormalization is EFT. Remember that? Except here, I don't have any other interactions. So I'm just going to call this counter term 1/2 delta m squared phi squared. And this thing is conceptually at order y squared. It's there to make the two Lagrangians agree at this order. Okay? Make sense? All right? So now, if I'm setting this equal to that, then this term just cancels, obviously. Okay? And so the counter term, which makes the match, is just equal to this diagram plus this counter term, right? Yes, right? Great. Okay, let's calculate this. What is it? Well, remember, the purpose of this counter term, its purpose in life, is to cancel the UV divergence in that, okay? All right? So I'm going to do the simplest thing, the simplest, most practical thing, because I'm done with my conceptual version of renormalization. I'm just going to relax and use dim reg and minimal subtraction, okay? Because it works, all right? It's good. And once I do that, this thing is completely independent of the cutoff, yes? And what does it look like? Okay, what does it look like? It looks like y squared over 16 pi squared. And then, remember, since I'm doing the EFT, I'm going to be thinking as m, that this p is small, and I'm expanding in powers of p over m, or actually p squared over m squared, right? And so what is this going to look like? It's going to look like some number times m squared plus some number times p squared plus some another number times p to the fourth over m squared, and so on until I get tired. Yes? Because I did renormalized. I did it in my head. Okay? And these are just some order 1 numbers, which don't matter, so I don't want you to be distracted by them, which means I didn't calculate them. Okay? So this is just the standard story we've told before. I have an expansion in powers of energy over the mass. And so now I see what I have to do here, right? I have to choose this thing right here. Let me call this delta m squared effective, because it's a counter term in the effective theory. So what I find is that this delta m squared, so I also need to have actually a plus 1/2 delta z effective times a kinetic term, because there's a term here which is proportional to p squared, right? To make that match, I have to choose this thing, and to make this term match, I have to choose this thing correctly, right? And so I have that delta m squared is equal to some number times y squared over 16 pi squared capital M squared, and then delta z, this is the effective, okay, is equal to just some number times y squared over 16 pi squared. Okay, makes sense? Okay, so now here's the point. The point is that what's interesting is that this can be very large, right? If I'm imagining that capital M is many orders of magnitude higher okay, then the mass that I'm interested in for the scalar, well, this could be very large, okay? So let's make that concrete, okay? So let's suppose, because this term can be very large, I've got to be very careful about what is a physical mass and what is just some mass parameter, okay? I'm going to have to be very careful about that. So let me just say, in sort of physical language, what it is that I'm trying to engineer in this point. I want the phi physical mass to be some number, let's say 100 GeV, like the Higgs mass, okay? And I want the physical mass of the fermion, okay, to be about 10 to the 16 GeV. That's what I want, okay? And I want the coupling Y to be of order 1. These are very much standard model-like orders of magnitude, okay? If I have a standard model embedded in a gut, this is exactly the sort of orders of magnitude that I would have, okay? Great. So now, let's first of all, let's think about this. So what I claim is m phi physical is very well approximated by the mass parameter in the effective theory. So let me square it, okay? And the reason is that once I've integrated out this big, bad fermion here, there are no more large corrections inside the effective theory. They're gone because the big, bad fermion is gone, okay? So I have some small loop corrections, but I'm not worried about small things. I'm worried about huge things here, orders of magnitude. So the first thing I claim is that the physical mass is well approximated by the mass parameter in the effective theory, by which I mean m squared plus my delta m squared, which is y squared over 16 pi squared, capital M squared, okay, plus possibly some higher order corrections, order y to the 4th. We good? Yes? Actually, this number is not exactly this number because of wave function renormalization, but it's of order that number, okay? So if you don't know what I mean, that's an exercise for you, okay? Put in some pretend numbers here and find out what this number is as a function of those numbers, okay? All right, but this is what we get, okay? And what about the physical mass of this big fermion? I claim that that is of order that is very well approximated by the mass parameter in the fundamental theory, because there's no big corrections there, they're just small corrections, okay? So what I really want is a hierarchy between the effective mass parameter and the fundamental mass parameter, okay? But now you see I have a problem, okay? Because if I look at this equation, I want 100 GeV squared to be equal to this thing right here. Okay, so I'm going to look at this equation, okay? This equation says 100 GeV squared, that's m effective, is equal to m squared. I don't know what that is. I'm just going to leave it blank. And then what is this? I know what this is, okay? This is a factor of about 10 to the minus 2. This is 10 to the 32. So this is 10 to the 30 GeV squared. Okay, let me write this as 10 to the 4th GeV squared. Okay? All right, and then there are higher order corrections here as well. Everybody see what I'm doing? Right? And the issue is that this number is 26 orders of magnitude bigger than this number. Okay? But there's no problem, right? There's no problem because I have this parameter. This is the fundamental mass parameter that in the Lagrangian that I started with, and that could be anything. So I'm going to take it to be minus 10 to the 30 GeV squared plus this tiny little amount, and that's it. There's no problem, right? Well, I have to tune this thing to 1 part in 10 to the minus 26. Okay? That's just the fact. And so now we should ask whether this is a problem. Okay? And I think you know what the answer I'm going to give. I'm going to tell you that, damn right, this is a problem, okay? Because what are we doing here? Okay, we're doing physics, I think, right? We're not playing games. We're saying that I'm taking this theory seriously. This is probably not the fundamental theory of the universe. This is probably another fundamental theory. This is kind of like the condensed matter guy taking the sample out of the, whatever it is, the fabrication machine, and checking the doping fraction, you know, and when they dope it different ways, they can get different values for these parameters, right? And what this is saying is that to get a big hierarchy, we need to be very specially close to some special value, okay? All right, in fact, what is this special value that I speak of? There's some sort of little m star where something happens, okay? So let's look at this theory in this space of the fundamental parameters, capital M and little m squared, right? Those are my fundamental parameters, okay? Now, I'm interested in this very special point that I'm talking about here, and so that's happening where capital M is of order 10 to the 16 GeV, okay? And how big is little m? Well, it's the square root of, it's the square root of 10 to the 30. It's 10 to the 15 GeV, right? So this thing, since I'm writing m squared, I'm saying this is 10 to the 15 GeV all squared, okay? Just so you can read. Okay, anyway, that's the number, okay? And then, okay, I want to live somewhere here. But now, what is this actually? What I claim is that in this theory, what happens if m squared is really, really large? What happens? I don't know, I just get some heavy field phi. What happens if I make m squared smaller and smaller? I have a negative mass squared. Phi gets a VEV. That's called a phase transition. Remember phase transitions, right? Okay, and so in fact, what I actually have is something like this. Down here, I have the VEV of phi is 0, but then if I cross this line, I have the VEV of phi is not equal to 0, and this is a phase transition line, okay? And where am I trying to sit if I'm doing this? I'm trying to sit within a factor of an accuracy of 10 to the minus 26 on this phase transition line. So this is exactly like the doping thing, okay? Changing the doping is like changing these parameters here, okay? I don't know where they came from, string theory, Murray-Gell-Mann, I don't know, okay? But if you change them even the tiniest bit, you're somewhere way off this phase diagram here. You get my point, okay? This is my point, all right? So at this point, you know, you can imagine, I can very well imagine, because I've had this conversation with people, some old school theorist says, this is all nonsense. This is all complete nonsense, because the parameters of this theory are the renormalized masses, okay? They're the physical masses. Those are the fundamental parameters, okay? And you can compute everything in terms of the renormalized masses, and everything is finite. You know, this is all garbage, okay? You know what I would say to them? I would say, okay, so you're saying we can never learn anything about any of the parameters in the standard model, okay? And in fact, what I'm going to be telling you is that within the standard model, we understand a lot, okay? In the same way that you can understand a lot about condensed matter physics, the details depend on the details, but the gross features, you know, are robust and make sense. But in this case here, I don't want to give up on ever understanding anything more about the standard model, and I hope you don't, okay? All right. Okay, so I'm done with that. So yes, questions, good time for questions. Oh yeah, you can change the theory. Yeah. Yes. Yes. You can make y, I don't know, 10 to the minus whatever we need, 10 to the minus 15 or something like that, okay? But then what I would claim is that this theory is just not going to be able to explain anything. So for example, in a grand unified theory, the whole point of grand unified theories is that the couplings unify, okay? And that they become non-zero. They're therefore nothing like 10 to the minus 15, they're like order 1. So, you know, you could also try to say, and this is something people have said, they've just said, well, maybe the standard model is all there is. So it's pure religion, what the parameters of the standard model are. And again, I would say to them, okay, so you're saying the thing, we'll never understand anything about the standard model, particle physics is an end. It is a hypothesis, but to me, it's like saying there's no evolution and there's somebody just, you know, twiddling the dials or something. It's not very predictive, it doesn't, you know, and I don't believe it's true, okay? And also, we have to understand, eventually, we have to understand dark matter, we have to understand neutrino masses, we have to understand inflation, we have to understand baryogenesis. I don't see how the standard model can be the end of the story. Right. Of course. Who cares about this model? I'm just using this to illustrate unnaturalness. So at the very last lecture, I might talk about some naturalness, and the bottom line of that, I'll just give it away, is that we don't know how to make the standard model natural. Okay? That's the puzzle. Okay? That's the puzzle that I'm trying to communicate to you in these lectures. And I think it's a very deep and difficult problem, and it may be something that will take generations, you know, but I think, in a way, I really think all of you should be thrilled with this situation. You know, if supersymmetry had been discovered, it means some old guy got their Nobel Prize, and your work is just to dust a little bit around the edges and figure out the SUSY parameters while they bask in their glory. But here, those guys are probably totally wrong, okay? And so the field is wide open, all right? I understand it's hard to make a career out of thinking about this problem, but I think that it's still there, and we shouldn't forget it. We shouldn't pretend it's not there, and we shouldn't forget it. Okay, so any other questions on this? If anybody else wants me to rant at them, I'm happy to do that. So thanks for being patient. Okay. All right, so I'm actually now going to go, as I said, I'm going to be skipping around here because I have to. So now I want to talk about another aspect of symmetry, which is very important and often not discussed. And what I'm heading towards now is I'm going to try to explain that, as I said, within the standard model, we have plenty of hierarchies. We have a lot of them, okay? And I'm going to claim that we understand them. And I have to tell you, to explain what I mean by understand, I have to tell you a little bit more about symmetry. And the thing I'm going to talk about is something called spurions. Okay? Just raise your hand if you've heard of spurions before. I'm just curious. Oh, good. Okay, but not everyone, some people. Okay? Good, but I'm going to talk about it anyway. Okay? So what is the idea of spurions? The idea is to extend the action, just extend symmetry transformations to act on parameters of the theory. Okay? All right? And when they act on parameters, I call the parameters spurions. Okay? And the reason that this is useful is because, of course, if I have a symmetry transformation acting on a parameter like the electron mass, well, the electron mass is a half an MeV. It's not going anywhere, right? And so it means that the parameters break the symmetries. The symmetries are not symmetries anymore because the parameters transform under them, and they're numbers. They're like vevs, right? They break the symmetry. But the point is then that the physical predictions of the theory are now covariant, right? They're not invariant under the symmetries anymore, but they are covariant with the parameters transforming along with everything else. That's the idea. That's the basic idea. Okay? So let's understand this with some examples. And the first example of a spurion that you actually know about, even if you don't know that it's a spurion, is just dimensional analysis. Okay, so let me explain it in the spurion language. The idea is I have a symmetry where I rescale all lengths by some parameter lambda L, I rescale all times by some parameter lambda t, and I rescale all masses by some parameter lambda m. Okay? So this acts on the parameters of a problem, right? So for example, if I have the world's most famous example of dimensional analysis is a pendulum, right? So I have some mass m, some length L, and I have some gravitational constant like this. Under this transformation, L scales by lambda L, right? The mass, of course, scales by lambda m, and the gravitational acceleration scales by lambda L over lambda t squared. Okay? So it's definitely not a symmetry. The length, the mass, and g are all changing. Let's say I'm interested in the frequency of the pendulum. Well, the frequency of the pendulum also transforms, right? It transforms as 1 over lambda t. Okay? And now, if I want to write omega as a function of these things, this tells me that the only thing I can write is some number times the square root of g over L, right? I actually couldn't decide whether it was L over G or G over L for a little while. All right, okay? All right, and notice that we actually expect this number to be order 1, okay? If these are all the important parameters in the problem, and there are no other large or small numbers in the problem, I would expect this to be order 1, okay? Of course, I cheated here because there is another dimensionless parameter in the problem, which is the starting angle. And Galileo, when he did this, he just assumed that it was independent of the starting angle. And he confirmed it experimentally out to theta naught equals pi over 2, kind of interestingly. Anyway, okay, but this is an example we know, right? Okay? Okay, so let's see, well, how is this useful and how is this connected to naturalness in quantum field theory, okay? So I want to start with, I'm going to now start using this. This is going to be useful to try and understand naturalness within the standard model. So that's where I'm going back up to naturalness now. I want to talk about the different mass hierarchies within the standard model, right? Because if we look in the standard model, what does it look like? So at an EV, we have condensed matter physics, or we have atomic physics, right? Then we get to 3 orders of magnitude keV, roughly that's where we have nuclear physics, right? And then at the scale of MeV, we start having relativistic electrons, and so we start seeing relativistic quantum electrodynamics. At a GeV, we see the strong interactions, right? And now we're just starting to explore the TeV scale, right? And we have masses all over the place here, right? So we have the electron mass is sitting here, you know, the muon mass is sitting here, we have pion masses, you know, sitting here, we have, you know, there's just tons of mass hierarchies here. And what I'm trying to say is that if we stick to below the TeV scale, all of this is perfectly understandable. There's no mystery about why there are large and small numbers here. That's what I want to explain, okay? So let's start talking about some of the mass hierarchies within the standard model. So I'm about 10 minutes out. Organizers, do you think I should stop for questions or should I keep going for a bit? I'll continue, okay? Guys, please interrupt me, okay? And I'll stop, I'll probably stop in about 5 minutes or so that we can, you know, to get a break. I don't know, we'll see. Okay, so the ultimate hierarchy, first of all, the ultimate hierarchy in the standard model is that the photon mass is exactly 0. Actually, we don't exactly know that it's exactly 0, but it's incredibly small. In fact, it'd be fun for you to think about, what do you think is where do you think the bound on the photon mass comes from? It's kind of fun to think about it. Anyway, it's incredibly small. It's basically 0. So what's going on? Well, they're here. I claim there's no mystery whatsoever. In fact, as Newton has been telling us, you know, a photon has 2 helicity states, okay? And that means that it is a 2-dimensional multiplet of the Lorentz group, right? The Lorentz group transforms a single photon state to some other single photon state, and basically there are two components, and in fact, they just, in the massless limit, they just transform. There's actually two one-dimensional transformations even, okay? But it's a very specific transformation of Lorentz. But on the other hand, if I have a massive, if the photon were massive, right, there would be three helicity states. Okay, and so the helicity is the momentum dotted into the spin. Let's say not angular momentum, but spin, normalized by the momentum. And in the massless case, we have plus or minus 1, and in the massive case, we have 0 and plus or minus 1. Okay? All right? And so if we ask, okay, is this somehow sensitive to having different weird things in the UV or changing parameters? The answer is no, because 2 is not equal to 3, so you can't change a 2 into a 3 by just changing some parameter, okay? So there's no mystery here, all right? The exactly massless photon is perfectly okay, all right? Okay, let's talk about something a little less obvious, okay? And that is that I'm going to pick the electron mass. I know that the neutrino masses are lighter, just hold your horses, okay? But it's certainly the electron mass is smaller than the muon mass, and that's smaller than many other things in the standard model, okay? So is the fact that the electron mass is a lot smaller than other things, is that natural? So let me just discuss this within QED, where I have both an electron and a muon. The mechanism is the same in a more complicated model like the full standard model, okay? And so the idea is that I have just, you know, a kinetic term and a mass term for both the electron and the muon. If I look at the kinetic term for the electron, I have, it just basically comes down to a separate kinetic term for the left and the right-handed vial components of the electron field, okay? But the mass of the electron, right, is a coupling between the left and the right-handed vial fermions, right? This is something you know. And what I can notice is that I can define a symmetry such that EL goes to e to the I theta EL, and ER goes to e to the minus I theta EL, okay? And under this symmetry, the QED Lagrangian is not invariant, okay? Because why? Because this term right here transforms as e to the 2I theta times itself, okay? But that's intentional because I want this ME now to be a spurion, okay? So I pretend that it's I allow it, this parameter, to transform as e to the minus 2I theta ME, okay? On the other hand, this transformation only acts on the electrons, okay? So all the other parameters of the QED Lagrangian are invariant under this symmetry. The muon mass is invariant under it because the symmetry doesn't rotate the muons, okay? And the gauge coupling is perfectly, let's call it E. The gauge coupling is invariant, okay? So now, why is this symmetry useful? Because I could worry that somehow the large muon mass is going to feed into a large electron mass, just like I found in my gut-ish model, okay? Okay? And so I could worry that I could get a correction to ME that depends on the muon. It could come from some two-loop diagram, for example, something like this, okay? An electron and a muon, okay? This is a hard diagram. It's two loops. Woo-wee, okay? And I could imagine that there's some finite contribution. Forget about, we renormalize, okay? Blah, blah, blah. But there's a two-loop factor here, okay? And then why couldn't there be a correction to the electron mass like this? Well, this symmetry makes it obvious that there is not, because all of the predictions of QED have to be covariant under these transformations, right? And the electron mass transforms and the muon mass does not. So this is just not allowed. Not at 2 loops, not at 3 loops, not at 4 loops, not at 8,500 loops, right? Okay? So in this sense, okay, we understand that this sort of thing can't happen, right? And yeah, I'll just say one last thing. Then, and we can phrase this another way, which is sort of a more traditional way to frame this. I could say that actually, if the electron mass goes to 0, then I actually have a new symmetry, right? Because this symmetry is only broken by the electron mass being non-zero, right? So if the m electron mass goes to 0, then I have a new symmetry, okay? And in fact, just by this same kind of argument, this new symmetry actually guarantees that ME is exactly 0. As long as the symmetry is not broken, M electron will be exactly 0. It's just another restating of this same argument, right? Okay? And that means that this is robust, right? Because simply the statement is that if I have an exact symmetry as ME goes to 0, if I want ME to be small compared to some other mass scale of interest, I just have to require that that symmetry is in some sense approximate, okay? So therefore, so an approximate symmetry, just loosely, okay, approximate symmetry will then imply that ME is approximately 0, okay? So this is not very quantitative, okay? The spurion analysis makes this more quantitative, as we'll see, okay? But this is sometimes called 't Hooft naturalness, okay? Because 't Hooft articulated this among all the other things that he did for us. He also articulated this idea of naturalness, okay? Okay, so that's, I think that's, I'm going to stop there. So, yeah, I'll stop there and answer any questions.
So when you talked about this new transformation, is this the usual U1 symmetry?
Yeah, this is the chiral U1. So in the Dirac language, if I take the Dirac E field, this would be something like e to I theta gamma 5 E.
Okay,
so this would be you would call this a U1 axial symmetry that acts only on electrons.
Oh, so it only acts on the electrons.
Only on the electrons.
You impose it.
Well, so it's because I'm a clever theorist, okay? So these spurious symmetries, right, I mean, I didn't make up the Lagrangian for QED, and to be honest, I didn't make up the symmetry either, okay? But some theorists came up with this. Maybe it was 't Hooft, or maybe it was older than that. But the basic idea, I'm sure it's older than that. I mean, people knew about these approximate chiral symmetries for a long time, and I think this point was largely appreciated. I think 't Hooft really, you know, put it in a general context. But yeah, this is an axial U1 symmetry that acts just on electrons, okay? And if you think about how this symmetry acts, you realize that it forbids things like this with no calculation whatsoever, okay? In this particular case, it's actually not that hard to show that this diagram or any other QED diagram cannot possibly give you an electron mass by looking at the details of the diagram, okay? So I'm not saying, but in a lot of other cases, it's much more non-trivial what the spurion analysis tells you.
So essentially what this analysis says is that if you consider the mass of the electron to be a spurion, then this type of diagram is forbidden. But if it's not a
any
spurion,
type of diagram, any type of diagram, you know, to all orders in perturbation theory like this will not give you a correction. Another way to say it is that the electron mass is multiplicatively renormalized, okay? If I have an electron mass in here, this is perfectly okay.
Yeah, sure.
Okay? And in fact does happen. So if you think there's a super slick way to see that there's no mu here, well, just know that this diagram actually does give you a finite correction to the electron mass.
Okay, so, but only if you consider the electron mass to be a spurion. Under the usual...
Well, this is, the spurion is just something I do as a theorist to make things clear.
Also, this type of correction to the electron mass does not exist in the standard model. Like,
Period.
Period.
Period. And I show that using a spurion trick. It's just a trick. It's a theory trick. It's a theorist's trick. Maybe we can discuss more later. I think somehow the philosophy has gotten lost. But this is just a trick. It's just a theory trick. They don't really, ME is half an MEV. It doesn't actually transform under anything. But if I pretend that it transforms, I can show that this can't happen.
Okay.
Okay. I think maybe I've done the best I can on that. Maybe we can talk more, okay?
Can you show that the term with ME instead of MU is actually allowed?
The one with ME,
Yeah, why is it allowed from the
well,
Fourier
because this transforms in the same way as that, right? Because this right here, delta ME, is also a coefficient of the same thing, and so delta ME has to transform the same way as ME. Do you see that?
Okay.
Because it's multiplying exactly the same thing. But the muon mass is not multiplying any electron fields, and so, sorry, so I keep doing it. This is not allowed, right? Okay, but the one, let me just, since people keep asking, so then, on the other hand, I do get effects like this. In fact, I even get them at one loop, but anyway. This does happen, okay? And this is perfectly allowed because delta ME transforms the same way as ME.
So we could keep making more spurion definitions. And
Oh, okay, you don't need to go to my lecture tomorrow, okay? Because that's what I'm going to be doing. We're going to be doing spurions all day, okay? I mean, yeah, we're going to do spurions for everything, okay? You can learn a lot. That's the point. This is just the tip of the iceberg. You can learn a lot. And this is something you should absolutely do if you have a model, you know, and you're trying to understand what can happen and not happen in your model. This is extremely useful.
So it's me. Sorry, but I can see how the approximate symmetry can relate the mass proximal to zero. I mean, there is kind of a factor to show it, because when we have the symmetry, some terms are forbidden and some terms are protected by symmetry, and I kind of can see that by the math. But in approximate symmetry, I can't see that. Can you explain me again, please?
Okay, so let me just say that this right here, all this stuff about the approximate symmetry, I was trying to relate it to a more conventional formulation of this called Tooth naturalness, and perhaps I could have done a better job explaining this, okay? But my real point here is that the spurion, I think the spurion way of looking at it is superior, okay? So what one is trying to get at with this, okay, I think is more systematically understood in the spurion language, okay? So for example, if I look at this thing, which is allowed in the standard model, okay, you might think that this is just some dimensionless factor that I could never get from a spurion analysis. But you would be wrong, okay? There's a spurious symmetry which even allows me to estimate this factor, okay? I don't know if I'm going to be able to cover that, but my point here is that the spurion way of looking at things, I think, is the most systematic way of understanding the role of symmetries that are not exact. Okay? Yeah. Sorry, was that okay, or? Okay.
I propose we have one more question and then we go.
Yeah, we have the
break
Q&A.
and then
We have the
the
Q&A, right? So maybe we need some people need a break. Not me, but, you know.
So this is like a global symmetry of the Lagrangian, so you also should have an associated conservative charge.
Well, no, because it's actually broken, right? So, right? I mean, the symmetry is actually broken. If this was a field, okay, if ME was a field, right, which actually kind of is in the standard model, right? We know that the electron mass is proportional to the VEV of the Higgs field. Then I could try to extend this to the action on the Higgs, And then, if it was an exact symmetry of the full theory, I could construct a Noether current. But the fact is that this is 1/2 an MeV. So the symmetry is broken. It's still useful, however, because if I pretend that it's a symmetry, then things are covariant, okay? So let me ask for something, because I have a sense, at least with 2 people, I feel like maybe this message hasn't gotten across, and as I said, I want to start doing spurion analysis all day. So please come and talk to me, maybe now at the coffee break or something, and I'd like to understand. I think I would like to try to, I think I'm sort of repeating myself and not saying something new, and I'd like to talk to you and see if I can come up with a better way to explain it or understand where the misunderstanding is better, okay? All right. Yeah, thanks.